All right, everybody, welcome in. I think we're good here. Looks like, am I a little blurry there? Let's see. A little better. Okay, welcome on in. So as we get started here, we had the holiday on Tuesday, so there was no class. Right, the whole campus is shut down on Tuesday. Um, so hopefully you're moving forward with getting your test taken care of. Either I know many of you already took the exam. Some of you still have appointments today or tomorrow. A couple people are taking the exam as we speak. That's okay. Just make sure you're getting it done. Make sure you're getting it taken care of. So is there any questions before we get started? Anybody have questions about anything at this point in the course? No? Okay. Feel free to throw them out there if you have some questions. Couple things I've been getting. Basically, I've been handling a couple issues, help people get their testing taken care of this week. So hopefully that's sort of settling down. I have had a couple of questions about the bookstore, so or about getting the actual license. So hopefully, I know most of you already got that done. There's still a few people that are kind of waiting on getting that license taken care of. So the thing is, we don't handle that, right? So that goes through the bookstore. So you have to go through the bookstore, and if the bookstore tells you to go to the lending library, then go there. But that's the process that you have to go through. So make sure that you're following that process, right? Unless you want to pay full price for the homework. I mean, that's an option. You can do that, but most people don't want to spend whatever it is if you don't have to. So that's sort of your options. There are certain things at the campus that we just don't handle, right? So stuff that's handled by the bookstore is not handled by the professor. So I mean, I don't have codes. I can't give out codes if I wanted to. So you have to follow that procedure that's stated. Basically, the whole class is like that, right? If you just follow the procedure that you're supposed to, then things should work out fine. Let's see. When will chapters 4 through 7 be open? That's a good point. I'll open those later today, or I'll at least open part of it so that you can move ahead with chapter 4. So let me make a note of that. Good comment. So I'll at least open chapter 4 and 5. I know the very last chapter that we do in the course, I still have to make a few videos for. The very last one we do, chapter 8. I still have to make a couple of videos for those, but that's a few weeks away, so I still have some time to get that done. But I should be the other ones, I believe, are all ready to go, so I'll just double check them, and then I'll open chapters at least 4 today, and then go forward from there. I'm going to grade the last few assignments. I was kind of waiting to make sure everyone had their stuff in and everything was all collected, but I'll start going through. I'll grade a bunch of the Canvas assignments. Let's see. Someone says they changed my time slot, so I only have 15 minutes to test. Is that enough? You should have more than 15 minutes to test. The test, they're supposed to give you 2 hours. So they might have changed your time to a different time slot, but at least they won't be restricting you to 15 minutes, I don't believe. That's not really doable. So I would make sure that you take more than 15 minutes to do the exam. There's a question in chat is what I'm responding to. So they are supposed to give you a 2-hour time slot in order to get that done. Let's see, question over here. Oh, when are you going to be able to see your grades? That's great. So basically, there's people that are going to be taking the test until late Friday. So on Friday, I'll collect those tests, and then I'll start grading them. And then I will post your grades in the XYZ homework. I'll create a column called Exam 1 or something like that, and then I'll put your scores in there, and then you'll know how you did. So hopefully by Monday, you should be able to see those scores. Maybe it will be Monday or I don't know, early next week is what I'll say, is they'll be in there. They might be sooner. I might get them all done Friday. I'm not really sure. Since I can't really collect them until the weekend starts, then that means they're not really going to get graded possibly till the beginning of next week. So early next week, you should be able to see how you did on the exam. and then we'll go from there. Okay, these are all good questions, so hopefully we're getting those answered. If you have any other questions, feel free to throw them up, and I will take a look at them. Otherwise, we're going to move ahead. So today I'm still talking about Chapter 3. Some of you took the test on Chapter 3, but Chapter 3 is a really important chapter, so I want to make sure to cover some things that are very easy to miss. Okay, and that's because, again, I know I've talked about this earlier in the semester. Sometimes people, and actually this will be relevant to a few different things we talk about today, but people get so hung up on doing math problems and memorizing how to do a math problem and the mechanics of going through and, say, solving an equation. And those things are very important, but it's very easy to think that's all math is. And the reality is that's a lot of why people hate math, because they go, I don't know, you just memorize how to solve some equation, and I never even have to solve that equation, so what's the point? And you're kind of right in some ways. What is the point, especially since now we have software that at this point can solve a lot of math better than a human can. And the way things are looking with AI in the next few years, it will be able to solve most math better than people. So the reality is, when you do a lot of this stuff in the real world, you're going to be using software to do it. So then, you can make the argument, well, why do we spend all this time learning how to solve equations if software is going to do it for me? Well, one, you want to understand what steps are being taken by the computer, because sometimes you have to make adjustments in order to get it to do the thing that you want it to do. But also, again, it's that interpretation. It's understanding the big picture, what's actually happening with the math, right? You can go into Wolfram Alpha and give it an equation and say, solve this, and it'll tell you x equals 3, and you go, hey, x equals 3. But, if you're working on the job, your boss doesn't want to know that x equals 3. They want to know the answer to okay, what does that mean? What are we supposed to do in terms of a business decision? Or if you're an engineer and you're designing some kind of circuit or some kind of piece of, whatever, an elbow or something that's, going to be a joint for something, x equals 3 is great, but it's useless to you unless you know, what does x equals 3 mean? What is the interpretation? What is the point? What is the whole reason we did any of this? And there's a lot of that can get lost in Chapter 3. So again, it's not just about being able to solve equations. It's about being able to actually understand what you're doing, what you're talking about, right? So that's a lot of what we're going to get into today. So where are we? Right. Oh, right. So I've got the book here. I think that's pretty good. So I'm going to end up going through a lot of these. Chapter 3 has a lot of little details in it that are easy to miss. So a lot of what we're going to do today is go through those details and try to explain them, because I know sometimes, just for students that are new to high-level algebra, trying to read these definitions and these theorems in the book can be very confusing. You just look at it and go, I don't know. It just looks like a bunch of fancy writing. I don't really know what any of this means. So I'm going to try to make sense of a lot of these definitions and theorems so that you can actually understand the big picture, hopefully start piecing together all these things in this chapter to sort of understand the big picture and what the point is of why we're doing this in the first place. So 3.1 I skipped for now, just because I think it's sort of stuff we've looked at, or I think that you can pick up pretty quickly on your own. I want to dive into some of the deeper stuff so we can kind of make sense of it, and then we'll see how much time there is for me to do more, right? But we'll sort of take a look at things. So starting at 3.2, they take a step back, and there's a page here where it's largely review. They give you the definition of a polynomial, and then they give you a bunch of definitions along the way. All these bold terms are definitions that we've talked about previously, right? So we've got a polynomial function, and this looks real fancy, but all this is a function way of writing f of x. Let me make this a little bigger. F of x, that's what we oftentimes call our functions. It's just a coefficient times the variable to a power. Coefficient times a variable to the power, all the way down. And we talked about that earlier in this semester, that sort of sums up. That's every term in a polynomial. Even these ones at the end, this a1x is really a1x to the 1, and this a0 is really a0x to the 0, right? So every term in a polynomial can be written as a constant times a variable raised to a power. Okay. We've got the degree. The degree of the whole polynomial is the largest exponent that occurs in that polynomial. The degree of a term is the exponent that occurs in that term. Okay. Now, we generally write these in descending order. That is, we put the biggest exponents up front, and then we put them in order as they decrease down to 1 and 0, and we don't write the 1 and the 0 exponent, but, we decrease them down. So, in other words, the x cubed terms comes first, then the x squared term, then the x term, then the constant. That's what we call standard form, and you generally want to write things in that order. One of the things that I see people have trouble with in mathematics is they're very disorganized. And in mathematics, you just really can't be disorganized. You have to sort of be able to organize what you're looking at and work with it, right? It's the same thing. If you go into your bedroom because you're looking for something, did I leave my wallet in the bedroom? And you go in there and everything is nice and cleaned and orderly, and everything's where it's supposed to be, then you immediately go, oh, yep, there's my wallet on the nightstand. I guess I left my wallet over there, and you go grab it. But you go into your bedroom looking for your wallet, and everything's a mess. There's clothes everywhere. There's stuff all over the ground. There's like stuff from maybe old plates from when you're eating, and the room's just a disaster. And you're trying to find your wallet, and you can't because everything's in the way, right? It just makes it a lot harder. That's kind of how math is, right? When you're organized and orderly and neat, you're going to be able to do your work much, much more efficiently than when you're sloppy or lazy with a lot of steps, right? So, we'll get the question sometimes, do I have to put it in standard form? Do I have to put it in this order? And the answer is, it's in your best interest to. You might think you're saving time by not doing that, but you're not. You're saving time by putting it in the right form and just going from there, because mistakes in mathematics are very costly. You have to stop, figure out where your mistake was, redo a bunch of work, and that takes a long time, right? So just in general, not just this section, but in all of mathematics from here on out, whether this is your last class or whether you're going through the whole calculus series, being orderly and organized with your math will make you much more successful than when you're messy. And I know people will say, no, it's okay. I'm the one. I work better when it's messy, but those people end up failing tests, so they don't really work better when things are messy. So do yourself a favor, organize your work, make it orderly. You're actually gonna save yourself a lot of time by doing that. Remember, the leading term is what we call the one with the biggest degree. That's the one we should be putting out front. That's why they call it the leading term. Okay. So things that have a square root in them, like over here, that's not a polynomial. Things that have a variable in the denominator, that's not a polynomial. Polynomials, look like this. And this is a polynomial because if we multiplied this out, if we distributed that 2s in there, then it would look like something up here, right? So that's still considered a polynomial. All right. You can tell polynomials pretty quickly from looking at the graph. Generally, a polynomial is a smooth, continuous curve with no sharp edges. So you can tell immediately which ones are polynomials here. This one has a sharp edge, like a sharp corner to it, so that's not a polynomial. This one has a discontinuity to it, so that's not a polynomial. These two in the middle are polynomials. They're nice, smooth curves. For those of you going on to calculus, you'll love when you have to deal with polynomials, right? You might not like them in this class, but in calculus, you're going to love them because this behavior of polynomials, where they're smooth, continuous curves, means they behave very nicely, and they're the easiest functions, some of the easiest functions to deal with in calculus, right? Like I say, you'll cheer when the problem on your test is calculus involving a polynomial. You're going to go, oh, good, I definitely can do this one, right? So you want to get comfortable with polynomials, and you want to understand the things in this chapter because it's going to make if you're going on, it's going to make that a lot easier. So in the book, they kind of talk about polynomials of the form x to the n because we can sort of simplify. A lot of times if we're talking about end behavior, then the degree, remember the degree of the polynomial determines the behavior, the end behavior of the whole polynomial. So for instance, like right here, we can see they're showing us well, let's look at it over here. where was it where we talked about it? They talk about transformations, and transformations, I'm trying to remember, where exactly did we do? We did transformations back here in the last chapter, so I had this transformations of functions, and we had a video, and I had a worksheet for you to work through, which some of you may have done, some of you may not have. Those of you who did the worksheet are going to understand all this discussion about transformations much better. It's going to you're going to go, oh yeah, that's just like the thing we did before. That makes a lot of sense. Oops, that's not what I want. I want that. So the transformations work like you would think. So here, right, just all the work you did in transformations, it just applies to polynomials. So right here, if I look at this, I go, let's see. Well, that's an x minus 1. Oh, that should be a, so ask yourself if you know this. If not, go back and work on that, watch that transformations video, and then work through that worksheet using Desmos. This should be a horizontal shift, right? In fact, it should be a horizontal shift to the right, x minus 1 to the 4th. So you think about, oh, well, what does x to the 4th look like? And then you do x minus 1 to the 4th. And sure, you could go over to Desmos and put it in Desmos and go x to the 4th versus x minus 1 to the 4th. And you could see that it's a shift this way by looking at the two. But obviously, it's pretty convenient to be able to look at it. See how I did that ahead of time without even having to graph it? I just looked at it and said, oh, that's a horizontal shift to the right. Excuse me. Excuse me. Allergies are getting bad. Right, so obviously, if you have two people working on a problem, and one person can just immediately tell the behavior of the polynomial, and the other person has to go get out a graphing utility, graph them, and then see, oh, it's a shift over to the right. One person is going to outperform the other person quite a bit, right? So that's very helpful to be able to just see those transformations. If we look at this one over here, I look at those transformations and go, make that a little bigger. I can look here and go, oh, well, that's like x cubed. And you should know those basic families of graphs. That's on that worksheet that I gave you. But you should be able to understand pretty quickly when something is a version of x squared or x cubed or a square root or an absolute value. You should be able to recognize those. So you go, okay, this is like x cubed, except the plus 1 shifts it vertically up 1. And the negative, that's going to flip the whole thing upside down, right? So again, we can go over here to Desmos and go, okay, we've got our x cubed versus our negative x cubed. See how that part flipped it? And then I go add the plus 1, and that shifts it up 1. So see how nice it is when you can do those transformations just by looking at it? That'll make you a lot faster. It'll lead to a lot less mistakes when you can just do that rather than being totally dependent on a graphing calculator or graphing utility to do it for you, right? So keep in mind those transformations. Whoops, here we go. One thing they point out at this point that I want to show you, I'll show you here on Desmos, is that as the degree increases, you get a little bit different behavior, but you get sort of a sharpening of the graph. So what I mean by that is we have our two basic graphs for polynomials. Here's our x squared. Here's our x cubed. Right, so you can see the difference. There's x squared. There's x cubed. Well, x to the 4th is going to look a lot like x squared, except notice it's a little like, it's increasing. It's a little skinnier. That's because it's increasing faster because it's x to the 4th. But it's a little flatter down here. So let's make this a little more extreme. How about x to the 8th? And you can see how it's flattening out at the bottom down here. So this part's getting less round. And then up here, it's getting more straight. They're just shooting up really, really fast. So that's a behavior that happens. If we make this x to the 12, or let's even go 16, you can guess what's going to happen. It's getting very flat. It's not sharp here. See how there's still rounded corners? But it's getting flatter and flatter here. And then these parts are getting sort of straighter and straighter. That's just what happens. So that's nice. That means what if, like, we have not yet looked at x to the 10th. But you can kind of make a prediction what x to the 10th is going to look like, right? something like that. It's not quite as flat as x to the 16th was. It's not quite as rounded as x squared was. It's somewhere in the middle. So at least you have that idea of what it looks like without having to go run to a graphing utility. So that's some behavior that gets pointed out in this section. The leading term test for end behavior, basically what we have, we talked about this when we looked at end behavior for rational functions. You have 4 possibilities for end behavior, and the great news is this is a really easy one to do. You don't really have to do a bunch of number crunching. So remember we had 3 cases for the end behavior of a rational function. We have, actually, was that in here? We did that. Either way, it doesn't really matter. So, sorry, I was just trying to remember if I mentioned something or not. So we've got the end behavior of a polynomial. So end behavior of a polynomial means what's happening on the ends. It's not talking about what's happening around the origin. It's not talking about our x-intercepts or our maxes or mins or any of that kind of stuff. It's talking about the ends of the graph. So if we look at it here, let's get rid of these functions. We're looking at something like this. End behavior is about what's happening on the ends as you go out, really, really large x values and really, really small x values. So think of x equals 1,000,000, 1,billion, 1,000,000,000,000. X being 1,000 nines in a row, right? Really, really big numbers. We want to know what's happening to the graph. So that's what we call end behavior. It's the ends of what is occurring. And with polynomials, there's really only four possible outcomes, right? Because each end of the polynomial either has to go up to infinity or down to negative infinity. So if you think about that, you have 2 ends, right? The left side and the right side, and each side has 2 possible outcomes. So that's 4 possible outcomes for your end behavior, right? So for instance, the end behavior here is that both ends shoot up towards infinity. The end behavior here is that as x goes to negative infinity along the x-axis, so think about like being on the x-axis right here and then just moving to the left. What's happening to our function? Well, the function values are shooting down to negative infinity. Whereas over here, if we're on the x-axis and we start going towards positive infinity, our y values are shooting up towards positive infinity. That's a description of end behavior, right? And that's one of the 4 possible outcomes. So let's look. Once you get the hang of this, it's pretty easy to piece together which of these it is. If you try to memorize everything, it's hard. Everything in this chapter is hard if you try to memorize it. But if you understand what's going on, you can just kind of reason your way through each time. So let me show you something just to convince you. See how we have x cubed, and then we have something like x cubed plus 12x squared minus 6x minus 3. So I've got this big polynomial here, and sure, it's doing different things inside the graph. Let's kind of come out a little bit. We can see there's different behavior coming on. This green one's just coming down, hitting the origin, and it keeps going down. This purple one's got some different things going on. But what I will tell you is the end behavior of these 2 functions is the same. How do I know that? Well, if we zoom out enough, we can see, oh yeah, you can kind of start to believe me. Well, if our x values are getting big, well, both of these functions are shooting up towards infinity on the right here. And over here on the left, both of our functions, as x goes to negative infinity, both of our functions are shooting down towards negative infinity. So remember, when we're talking about end behavior, we don't care what's going on in the middle. There are times when we want to know about what's going on in the middle, but not when it's end behavior. End behavior is like, what's happening on this end? Is it going to infinity or negative infinity? What's going on this other end? Is it going to infinity or negative infinity? And that's really the that's really what we're concerned about. Well, the reason that these 2 functions have the same end behavior is because remember when we talk about end behavior, we're talking about really, really big x values. Well, if you take an x value that has, say, 10,000 nines in it, and you stick it in these polynomials, this like -3 isn't really going to play a very big role, right? I put a 1,000 digit number here and I cube it. This -3 isn't going to make any difference, hardly. Neither will even the 6x or even the x squared. When we talk about end behavior, the term that decides, like it's kind of the bully, it just gets to call the shots, right? The one that determines the end behavior for this function is the x cubed, because it will be so much bigger than the rest of these other terms combined, they won't even really have much of an effect. They have an effect in the middle when x's are small, but when we're plugging in massive values for x, the only one that matters is this biggest term, which should be your lead term if you're writing your polynomials in the right way, hence the name leading coefficient test. So if we want to know the end behavior of this polynomial, we can just reduce it to x cubed and ask ourselves, well, what's the behavior of x cubed, right? So hopefully you know that already, but if you don't, think about x cubed. That's a variable to an odd power. Okay, so when I put a negative in, I'm getting negative numbers, but when I put a positive in, I'm getting positive numbers. Well, then if you think about it, if you're putting in really big positive values, so as x goes to infinity, then I'm getting out really big positive values. So on the right, our function shoots up towards infinity. And as I put in negative values, I'm going to get really, really negative numbers. So that's why they're going down towards infinity. So this purple function has the same end behavior as just the function x cubed. Okay? That's how you simplify that down. I see students try to memorize this chapter, all these things, and it just doesn't really work. So the 4 possible outcomes that you're looking for, like question 1, you ask yourself, does my lead coefficient have a odd exponent or an even exponent? If it has an odd exponent, then your two ends are going different directions. If they have an even exponent, then your two ends are going the same direction, is how it works, right? So then from there, you just get your 4 possibilities. They could be, also, and then remember our transformations, that negative in front flips it upside down. So putting a negative in front of that lead term will basically flip the behavior. So that gives you your 4 possibilities. If your lead exponent is odd and your lead coefficient is greater than 0, then you're going to get this x cubed kind of behavior right here, right? If your lead term is greater than 0, but your lead variable is even, so like x squared, then you're going to get this kind of behavior, like a typical parabola, right? If you have an odd exponent, but a negative out in front, it flips it upside down. And the same over here. If you have an even exponent, but a negative coefficient, it flips your parabola upside down, okay? So that means we can just look at the end behavior of some of these things, and we don't even have to graph it. We can just tell the end behavior. That's really nice, right? Like if I look at this one right here, g of t is equal to negative 2t to the 4th plus 8t squared. Without graphing that, I can know the end behavior of this because I know, okay, well, for end behavior, I'm only concerned about the term with the highest power, so I only have to worry about negative 2t to the 4th. Well, t to the 4th should be like t squared, right? So it's like a parabola, except it's a little bit, it's going to be flatter in the middle, and it's going to be a little steeper on the ends. The 2 also makes it a little bit steeper, but that doesn't really concern us for end behavior. And then the negative flips it upside down. So this should be like a parabola that's been flipped upside down and then just made a little bit skinnier. So that tells me that both ends should be going to negative infinity. Well, let's see. So negative 2x to the 4th, what was it, minus 8x squared? Oh, plus 8x squared, okay. Plus 8x squared. Oops, that's because I didn't make this a 4th like that. So we can see there's some interesting stuff going on in the middle. But let's take a look. Remember, I made the claim that we can say this has the same behavior as the leading term, which is negative 2x to the 4th. And sure enough, yeah, on the ends, they have the same leading behavior. Both ends are going down to negative infinity, which is what I predicted before we graphed the thing, right? So it's very convenient to be able to do that. Right. Okay, I think that explains that. Also, there's video in there on it. Okay, finding zeros and x-intercepts by factoring. So when you solve a polynomial equation, you're finding what we call solutions a lot of times. But when we call it, when it makes your function 0, which is the same thing, we call it a 0. So it's basically you're solving functions, right? You're taking a function, you're setting it equal to 0, and you're solving it. That's what we call these real zeros. So when you solve an equation and you get a real number solution, those solutions that you find are also going to correspond to your x-intercepts, which makes sense when you think about it from a graphical perspective. So let's just look at a couple things here. So we've got our function 2x cubed minus 18x, right? And then notice, like, you can walk through where they solve it for the sake of time. I don't want to go through all that. But notice you get 0, -3, and +3. Those are the solutions. Well, look what happens when we graph this. What was it? It was negative. Oh, it was 2x cubed minus 18x. So 2x cubed minus 18x. We get this thing. But look where those solutions are that we found. Here's 3. Here's 0. Here's -3. So when you solve that solution, or when you solve that function, you set it equal to 0 and you solve it, you get 0, 3, -3. Look, those become our x-intercepts, which makes sense because when you're solving the equation, when you set the equation equal to 0, what you're asking is, what x values give me a y value of 0? Well, that's what the graph is showing you. It's showing you when your y value is 0 that those are the x values. So there is this inherent connection between the solutions to an equation and the x-intercepts of the graph. That can be really helpful because if you know for sure the x-intercepts, that's going to help you solve the equation. If you know the equation, you just solved it, you already know the x-intercepts without having to graph it, which can be convenient, right? So now the books kind of make a good big point about hand sketching the graph of a polynomial function. And here's one where I know a lot of students go like, oh, what a pain. Why are they like pretending like I have to sketch graphs? And the reality is in the real world, you aren't going to sketch a lot of graphs. Why? Because we have Desmos. You just come to Desmos or some other graphing utility. Those of you when you get to that are going on with math, when you get to university, they'll have software for you to use, and you just graph the thing. It's very easy to do, right? This wasn't the case, say, 40 years ago. In 1980, when most people didn't even have a computer at home or a computer on their desk, right? There might be one computer that gets shared by people at work. It was a lot more difficult to graph something. So people had to graph these things by hand. But no one really graphs stuff by hand because it's faster and more accurate to just use a computer. So then why on earth are the books telling you about how to hand sketch things? The answer is because it takes all these different pieces that we're learning and puts them together and makes you be good at all of them, right? So that's really the key. When we have you sketch these graphs, it's not because you're going to be doing that in the workplace. You aren't. I mean, occasionally you have to sketch something just because you want to see what it looks like, but 99% of the time, you're going to use software to make a nice graph for you. But the reason we have you go through these is because it helps you visualize the thing that we're learning in the algebra, and then it forces you to see how it connects to the graph. Because like if I just give you a graph of something, say, here's the graph, understand it, just having it graphed doesn't mean you understand it. You just kind of look at it and go, I don't know, it kind of goes up, then it goes down, then it goes up again. But you want to understand all that underlying behavior, the x-intercepts, where is it increasing, where is it decreasing, where are the maxes, where are the mins, all that kind of stuff. You want to be able to pull that information out, and that takes connecting the algebra to the graph. So that's the key. Just kind of keep that in mind when it seems like a big annoying exercise. Why are they making me graph this thing when there's Desmos? Yes, we know there's Desmos, but it's important that you understand how these pieces fit together. So let me kind of go past that because those are kind of just follow the directions. Multiplicities. This is a big one. I know a lot of students in these college algebra classes will sort of not really understand multiplicity. But there are times when understanding the multiplicity is not only very important, but also can save you a lot of time. There's times where I'll give a problem in class and 2 students are working on the problem side by side, and 1 student finishes in like a third the time of the other student. And that's because the student who finished faster is the one who understood multiplicity and said, oh, you know what? I can make a lot of my work more efficient in this problem by using the multiplicities. And the student who didn't really understand multiplicities is doing it the long way, which is the hard way that takes much longer. So a word about multiplicities. So the multiplicity is the degree of a factor in a polynomial. Okay. So remember those factors in the polynomials. If you factor an equation and solve it, those factors give you the solutions. And we talked about how the solutions are the x-intercepts. So it makes sense that the degree of a factor in a polynomial should affect the x-intercepts of the graph, right? If you need to, just you can rewind what I just said 15 seconds and sort of listen to it again. But the degree of the factor in the polynomial changes how we see that thing in the graph. So for instance, we could have, here's a polynomial, f of x. F of x equals, let's just make something simple, x minus 2, x plus 3. So here we have a polynomial. This is a typical quadratic. Notice how our x-intercepts correspond to the factors, because if we solved this, if we set this equal to 0 and solve it, we'd get x equals 2 and x equals negative 3. And sure enough, that's the number showing up on our x-intercepts. Okay. Well, look what happens if I change the degree of this first factor. What if I take this x minus 2 and I make it a squared? Oh, now our x-intercepts are different. Something different is happening here. So that is that we change the multiplicity. The x-intercept that corresponds to x minus 2, namely this one at 2, now has what we call multiplicity 2, whereas our other factor still has multiplicity 1. So you can immediately tell if the multiplicity of a factor is even or odd by looking at the graph of it. So if you have even multiplicity, what will happen is the graph comes down, touches, and then goes back up. Like x squared, how it just sits on the origin, right? The graph comes down, touches the origin, goes back up. That's what we have here. Graph comes down, touches, doesn't cross, goes back up. And then notice this one that's odd multiplicity, it just shoots right through. It actually crosses at the x-intercept. So that can be helpful. So let's make a prediction. What if I make this a cubed? Oh, we still cross. Why? Because it has odd multiplicity. Odd multiplicity means you actually cross the x-axis. Even multiplicity means you shoot back up. We can see that if I take this and change this to a 3. Notice that now we cross at that x-intercept, right? Now you might go, well, why is this helpful? Who cares if we cross the x-axis or not? Well, it's one of those things where you're not going to need to think about multiplicity for every single problem you do. But there are times when you might look at a graph and go, ooh, that has even multiplicity. So instead of doing this long division once, I'll just divide it out twice, and I'll get rid of the 2 factors at once. And that's where you start gaining on the people around you, where you're being more efficient because you're dividing factors out faster, and they're doing it the long way, where they're doing it again and again and again. So that's the basics of multiplicity, right? So if you have this, where you have your your graph comes down, touches the x-intercept, and comes up, you know that multiplicity is even. We're not 100% sure if it's 2 or 4 or 6 or 8 or 10, but you know it's even, which is usually enough. Over here, odd multiplicity is happening where you actually go through the graph. Okay. For instance, so let's just say that you had a function like the following. Whoops, and I want to make this one like this. Okay, so here we have a graph, and I'm looking for zeros of this thing. And I go, okay, well, we've got them at 5, 1, and -3. And you go, ooh, but this one has multiplicity 2. Right? We can see that the x-intercept is 1. So it comes down, or it comes up, hits 1, 0, and then goes back down. So I recognize that's even multiplicity. So if you have to do, like we're going to do in a few minutes, where you do a long division, I could, instead of just factoring out x minus 1, I could factor out x minus 1 times x minus 1, which is x squared minus 2x plus 1. I could just divide that out. It'd take me about the same amount of time, but I eliminated 2 factors from my polynomial, while the person sitting next to me only eliminated 1. And then they're going to have to do the division again in order to eliminate that second factor. So just be able to look at these, and when something pops out as being even multiplicity, just look at it and go, ooh, that's even multiplicity, right? And you can sometimes save yourself some work. Okay, let's move ahead. Symmetry, you've got your even and odd functions. I feel like symmetry is sometimes overdone a little bit in this class. Like, books make a little bigger deal out of it than it needs to be. Like, symmetry can be important. Like in a trigonometry class, those of you taking trigonometry, all your trig functions have a symmetry. They're either even or odd. So it's really important there. In like a college algebra class, very few of your functions are actually symmetric. So it just doesn't come up very, very often. But you need to know if they're called even, odd, or neither. So I believe I think we talked about this a little bit last time. Basically, your even functions are symmetric with respect to the y-axis. So if I folded this paper over, this side would line up on that side. That's called even. Odd is when you can view it as either a rotational symmetry. If we rotate this graph 180 degrees right around this point, we just sort of spin it 180 degrees, it's going to line up on itself, right? So that makes it an odd function. Or you can kind of project through the origin and you see that you get the point on the other side. That's called odd. Most functions are neither even or odd. They don't have that symmetry, but you end up with both of them. You end up with all 3 kinds. Okay, we've got local maxima, local minima. These are also called local extrema, sometimes called turning points. So you have some interesting stuff going on here. We go through and sort of figure out how to find those. I forget where it is in here. There's a nice tool that can be useful in remembering is the number of turning points. Okay, so let me explain a little further. The higher degree of your polynomial, the more complexity that polynomial can have. So let's take a look here, right? The most basic polynomial you can have is I guess you can have a 0-degree polynomial. That's pretty boring though. You can have a 1-degree polynomial. That's a line. Okay, that's pretty boring. You can have a 2nd-degree polynomial. Okay, that's a quadratic. That's a parabola that we've looked at. Okay, not too bad. Once you start increasing those degrees higher and higher, you can get more complexity in your graph. So imagine we've got something like, and you've seen that from some of the examples today, 3x to the 4th plus 2x cubed minus 3x plus 4. So we're seeing a little bit more interesting behavior here. What if we make this a negative? So this doesn't just look like a typical parabola anymore. There's some more stuff going on. It's kind of some different shape, right? It's still a polynomial, but there's some different complexity going on. So one of the things to know about a polynomial is the number of turning points that it can have. is 1 less than the degree of the polynomial. So if you think about it like a quadratic, so this is just x squared, has 1 turning point, right? You're coming down, you turn, you go back up. It's 1 less than the degree of the polynomial, right? If you've got a more complicated, say x cubed plus 4x minus 7, something like this. We have a 3rd degree polynomial. How many turning points does it have? We come up, turn to go down. That's 1 turning point. Now we're going down, turn to go up, 2 turning points. Can there be any more? No, because a 3rd degree polynomial can only have the degree minus 1 turning point. So 3 minus 1 is 2. So we know we've got all the turning points. This can be helpful because if I'm looking at this graph, how do I know that off my screen the graph doesn't turn and like come back down again or have some more turns off screen that I can't see? Do I have to keep zooming out to infinity to figure out if I've got all the turning points? No, they're all accounted for. An x cubed can only have at most 2 turning points, and I'm looking at both of them. Therefore, I know no more of them are happening off screen. Okay. So that's just another like handy thing to keep in mind when you're looking at polynomials. Okay. Right. And then a couple basic things here. The number of real zeros of a polynomial function f of degree n is less than or equal to n, counting multiplicities. The graph of f can cross the x-axis at most n times. So what that's basically, what I'm kind of going to sum these up as, like I'm going to expand on this a little bit more than just they're going to tie it in later with another theorem. So basically what this is saying is that if you have a nth degree polynomial, it has n solutions. So if you have a 5th degree polynomial, that polynomial has 5 solutions. If you have a 3rd degree polynomial, that polynomial has 3 solutions. And you might go, well, wait a minute, we've done some problems where I solved a polynomial and there was less solutions than the degree. If you count multiplicities, like it says here in the problem, then you get the same amount. So you might have a 3rd degree equation and you solve it and you just get x equals 2 and x equals 1. But that x equals 2 actually occurred 2 times. So if you count multiplicities, you get all those solutions. So the number of solutions to a polynomial equation is the degree of the polynomial when you count multiplicities. Okay, that's helpful because sometimes students will solve, say, a 4th degree polynomial, and once they get 2 solutions, they stop. So either they just gave up or they thought they were done. Well, if you're solving a 4th degree polynomial equation, you're not done until you solve 4 solutions, right? You need 4 solutions in order to complete that thing. So it's handy to know how many solutions you're going to get. Okay, let's see. Where are we now? Oops, I wanted to be over here is actually what I wanted. Okay, division of polynomials I want to talk about a little bit. I don't really love a lot of times the way that division is handled in these algebra books. I think they take sort of a lazy and in some sense maybe even a irresponsible approach to division of polynomials. They go through and they do long division of polynomials, which I know sounds scary at first. Oh my God, we're going to do long division. I remember hating long division in the 2nd grade, and now we're doing long division of polynomials. It's the worst. Yeah, I'm going to, there's a question here. I'm going to address synthetic division in just a moment. Yeah, that's a good question about synthetic division because I have sort of a little, that's kind of where I'm going. I have a little bit of a rant about synthetic division. So here's the nice thing about polynomial long division. It will work every single time. Okay, and that's a great tool in mathematics because a lot of times we have a math tool that says you can use this tool under these conditions, or you can use this tool if this happens. But it's really nice to have a tool that just works every single time, right? You get this with polynomials, second-degree polynomials, quadratic equations. How do you try to solve a quadratic equation? Well, the first thing you try to do is solve it by factoring, right? Why? Because it's easy. It's easier, I should say, to solve a quadratic by factoring. And then sometimes you play with that quadratic equation. You go, oh, it doesn't factor. I guess I can't use factoring. So then what do? You go to the tool that works every single time, no matter what, the quadratic formula, right? So we pull out that quadratic formula. It's a pain to use, but it gets us to the answer every single time. That's kind of how division of polynomials is, except I think it's actually even worse where the reality is synthetic division doesn't work a lot of the time. There's a lot of times where synthetic division doesn't work. So there's the polynomial long division. I have a video on that in Canvas, so you can follow along. If we go, what are we dividing polynomials? I've got me right here doing long division of polynomials. There's another long division of polynomials. There's a synthetic division of polynomials video that I stuck in here. So if you're wondering, check that out in Canvas. There is, because I'm not going to be able to go through and do a complete example for synthetic division, but there is an example. Excuse me, I got the hiccups. There is an example posted here in Canvas. So to the person who asked, I'm gonna say check out the synthetic division example. And also, if you want more examples, you can definitely just go on YouTube and look up synthetic division, and there'll be lots of videos on how to do it. But where did the homework go? I lost it. Here it is. Not one window hidden behind the other. So polynomial long division is like the quadratic formula in that it will always work. And so that's why I prefer it. I don't see the point of learning two methods. If I have one that's going to work every single time and isn't really that much harder, then I'm just going to use it, right? And this is, so then we move into synthetic division, and this is one area where the high schools and the colleges tend to operate a little bit differently. A lot of times in high school, the teachers just want you to be able to pass the standardized test, so they're trying to teach you a way that you can remember. Doesn't matter if, and I'm not saying all teachers are like this, but in high school, sometimes this can happen. It's about getting students to memorize how to do a problem so they can get it right on the standardized test. We don't really care if they understand it or not. We just need them to be able to do that for the test. In college, we don't have standardized tests. We're more concerned about you just learning the material. Having you learn synthetic division but having no idea what you're doing is not really helpful. Also, so many students, they just don't really understand when to use synthetic division and when not to use it, which then leads to them using it when they're not supposed to, because they go, well, it's easy, or I'm just going to try to make it fit here, and then it doesn't work. So for some reason, I'm not sure why people in college still love synthetic division. Those of you going on to calculus will have teachers that say use synthetic division for this. I think it's overused because like with long division, it's easy to understand what you're doing, right? When you multiply two things, remember what you're ultimately doing is adding something up a bunch of times, right? If I say 5 times 13, then what does that mean? That means add 5 up 13 times. So you can think of multiplication as repeated addition. Well, then it stands to reason that you could think of division as repeated subtraction. Well, that's what you're doing when you do long division. You're just subtracting things off. You're subtracting groups of your factor off and keeping track of how many you're subtracting, right? It's just the inverse of multiplying 13 5s together. You're subtracting 5s off, and then eventually you count up that you subtracted off 13 5s. That sort of can be understood. Students will memorize synthetic division, but if you ever ask them, well, how does this work? I've never had a student successfully explain to me, oh, this is what I'm doing when I do synthetic division. It's just a sort of a trick they learned. Well, what's the point of learning a trick if you don't understand it? No real point, right? We can have a computer or software do that. right? And not understand what it means. We want to understand what's going on. So they give you here the division algorithm, which is really important, and mathematicians get all squirrely about the division algorithm. They love talking about it. But most people in a college algebra class aren't going to get too excited about it. Just sort of realize there's an algorithm, and when you're going through the division algorithm, what you're doing is you're doing repeated subtractions. You're keeping track of how many times you're subtracting, and that ultimately gives you your division. Right? So it walks you through pretty well on polynomial long division. I have examples in the video in Canvas about long division, so go through and do that. You just want to be careful with remainder. I know some of you learned in the 3rd grade that when you have a remainder, you write R5. If you have a remainder of 5, that's not really mathematical. That doesn't really make much sense. So we write the remainder. There's really 2 details you have to keep in mind. One is how to write the remainder. And basically what you do is whatever you're left with as your remainder, you write it as that over the thing that you're dividing by. So see how down here they have negative 51 over x plus 2? That's because they took the negative 51, put it over the x plus 2, because this was your leftover that still needs to be divided by x plus 2. Okay. The other thing you have to look out for is see how right here they put a 0x squared in here? Well, if you notice when you set up long division, notice how everything's in columns. This first column is the x cubed terms. This column is the x squared terms. This column is the x terms. This column is the constant terms. That organization is really important. If you lose that organization, the problem just falls apart and it becomes a big mess. So what happens is if you're dividing by something that doesn't have an x squared term in it, well then where would you put this 12x squared? Where would you put these negative 12x squareds? You have no place for them. So if your polynomial is missing a term, we generally just put in a 0 times x squared there, or whatever variable term is missing, whether it's x squared or x cubed or x to the 4th. It just leaves you a space so that you can put those x squared terms in there. Okay, those are the only 2 things you really have to remember. How do you write the remainder, and what happens when you're missing a term? And the answer is real easy. You just put in 0 times that variable, and it gives you a lane for your, in this case, squared terms, the x squared terms. Okay, so it's pretty straightforward. Synthetic division is one of those things that you can memorize really easily, but what's the point of memorizing synthetic division? And then when someone says, well, what are you actually doing? You go, I don't know. I just memorized like a thing that a computer can do faster than me. So what's the point, right? So what happens for synthetic division is you take the opposite of whatever you're, like in this case, we're dividing x cubed plus x minus 1 by x plus 2. So you take the opposite of this sign, and we're going to write it over here. So in this case, it's x plus 2, so we put a negative 2 here with a little corner. And these coefficients are the coefficients that come from this polynomial. Notice how we're still putting a 0 there for x squared. If you don't put the 0 here, it's going to mess it up too. So you still have to do that step even with synthetic division. Okay. So you go 6x cubed plus 0x squared plus 1x minus 1. And what you do is you bring the 6 down, and then you multiply by this number. So 6 times negative 2 is negative 12. Then you add these. You get negative 12. Now you're going to multiply by this again and write the number up here. So negative 12 times negative 2 is positive 24. Add this column to get 25. Multiply by negative 2 gives you negative 50. When you add them together, you get negative 51. Now it's interesting to note how the numbers that we're seeing here should look familiar. Negative 51, negative 12, 6, 25. Those look familiar to when we did the problem up here using polynomial long division. Negative 51, 25, negative 12, 6. That's not a coincidence, because synthetic division is just a shortcut for doing the actual math. The problem is most people don't know what's actually happening. And maybe you go, well, I don't care what's actually happening. I just want to be able to do the problem. Well, here's the other issue with synthetic division. Let's see, I forgot where they listed them here. One drawback is you have to be dividing by something of the form x minus c. So it has to be something like an x plus 2. If you're dividing by a, say, 3x minus 2, you're out of luck. I mean, there's some work you can do to force it to work, but by that point, you've done more work than if you just use synthetic polynomial long division, right? So if you're dividing by something where there's a coefficient on the x, 5x plus 7, 4x minus 3, something like that, synthetic division is going to break down. If you are dividing by something where this isn't just an x, maybe it's an x squared or an x cubed or an x to the fourth or something, or a more complicated polynomial, synthetic division doesn't work. So there's a ton of cases where synthetic division fails you. It doesn't even work properly. And then when you do use it properly, you probably also don't really understand what you're doing. So my recommendation in general is that people use long division and just know it, because it works every single time. You don't have to worry about, oh, is this one of those cases where I can't use synthetic division? I don't remember. And then also you understand what you're doing. So I know some of the homework problems say use synthetic division. Feel free to use long division if you like. You will have calculus teachers. Those of you going on to calculus, you'll have calculus teachers that say use synthetic division here, and they'll want you to know it. Generally, you can still use long division if you want. If you're someone who wants to learn synthetic division, go ahead. So follow the video that's posted in Canvas. Also look at the examples here in the book. But I find synthetic division actually to be one of those things that students really like, because they go, oh, this is an easy thing that I can memorize. But actually it causes problems, because I'm known for putting division problems on the test that you can't use synthetic division, right? Like, that's just the thing I often do, because I don't like synthetic division. I'd rather know that my students know how to do actual division. So it's up to you. You can learn both, learn long division, whatever you like. Okay, before I forget, we better get to roll call, and then I'll talk about, I think we're probably ready for 3-4 at that point. Okay, so let's see who is here in Zoom. Okay, so just a heads up for people. Oops, what do we got here? Oh, and then there's a question in here that I can address. So just so everyone's aware, and I will post an announcement about this in Canvas, but at the beginning of next week, remember I talked about how I have to do drops and keep all the rolls clean and stuff like that. So at the beginning of next week, I'll be going through and looking at absences, amount of homework done, and people who did or did not take the test. And if you're deficient in those categories, and the case can be made that you're not really participating properly in the course in order to make a successful finish, then I'll be dropping a group of people. So please make sure that you are getting caught up on your homework in a way that I can at least justify, like, this person is reasonably close enough that they are still going to be able to can finish the course. Yes, they took their test. And also they're showing up to class. So please make sure you're doing those things. I know we're seeing a few people with a few more absences, but I do have to do drops here coming up. Okay? So I think, and just for the record, people I don't have for today, let's see, Eddie A, Cynthia C, Alejandro C, Daniel DT, Veda F, Sergio G, Laura G, I think a couple of these people dropped. Raymond L, Monique P, and Zali T. Oh, and that other person dropped. I think about 4 people have dropped. I need to update my record here just so I don't keep looking for those people. But yeah, so next week, once I have grades submitted and I can see who didn't take the test, and then I'll look at homework and see who's not really doing the homework and stuff like that. And then so just be aware of that. Make sure that you're largely caught up. Okay, Cynthia. Gotcha, Cynthia. Okay. All right. So, yeah, make sure about that. And then there's a question. After a discussion post is late, is there no way of going back to do it? Correct. Make sure you get those the Canvas assignments. Make sure you get them done on time. They can't really be done late. Here's the reasoning behind that. The Canvas discussions are usually timed for a specific reason, like preparing for the exam. Well, if you go in next week and work on the preparing for the exam discussion, it doesn't really make sense, right? Because why would you be working on preparing for the exam when you already took the exam this week? Or if you didn't, then you're getting dropped next week, right? So there's a reason that those Canvas assignments happen when they do, and doing them late just sort of like you could say, well, I could still get the points, okay, but you won't get any of the actual learning benefit from having done them. So that's why the Canvas assignments cannot be done late. They're usually targeted for a specific reason, whereas the XYZ homework, you have the late passes, and some people are using those late passes in order to get things turned in a little bit late. That's okay, because you still need to complete that work and get ahead, because if you don't understand that material, it's not going to help you in the next chapter when you have to use it to do part of a problem. So that's why you can do the XYZ homework late, but you can't do the Canvas assignments late. Okay. Yeah, that was a good question. Okay, looks like actually I only have a few minutes left. Let's see. Missing 1 or 2 Canvas assignments won't affect your grade in a huge way, right? That's why I try to point them out when they're upcoming. That I've been pointing them out in class so that people can make sure they know they're there, right? I think I've pointed out most of them so far. I've kind of given a heads up. Looks like there's one due tomorrow, right? So make sure you get that one in there. And then I'll be adding some as I release the other chapters. I'll be adding some discussions in there for students to participate with. So always just sort of look at there and then make a note of when the next discussions are due, and then just make sure you get them done on time. Okay? Okay, so with the couple minutes left, we don't really have time to get deep into stuff, but let's see. Oops, that's not what I wanted. Let's do this. Oops, it kicked me out. Let's see, back into 3. Yeah, so there's some, let's see. 3-4 and 3-5 have quite a bit going on. 3-6 and 3-7, I would say not as bad. 3-7, you're just sort of follow along the examples. But 3-4 and 3-5 have a little more of this theory we've been talking about. So I'd encourage you to look in the book and try to make sense of what you're seeing. Sort of already summarized some of this a little bit. There's the rational zero theorem. Watch one of the videos that are posted in order to make sense of that one. That one's a little bit confusing, but once you get the hang of it, you go, oh, it's not too bad. Right. Yeah, so that one's not too bad. But these are the steps that you use to solve those high degree polynomials, like the one that you have on the test. So make sure you can do that. See if there's anything I want to point out in 3-5. The fundamental theorem of algebra is really important. I kind of gave it to you already. Says every non-constant polynomial with functional coefficients has at least one complex zero. And then a consequence of that basically is what we talked about. The number of solutions in a polynomial equation is the degree of that polynomial, counting multiplicities. Okay. Yeah. Okay. I think you're good from there to be able to finish that. So things you want to do. We've got. Let's see. Let's look at the calendar and XYZ homework. You've got what? So you've got chapter 2 is due today. Hopefully you're well past chapter 2. Otherwise the test is going to be difficult for you. And hopefully you're at least into the you've been working on chapter 3. I hope that's due Monday. And then chapter 4 we'll talk about next week. Right? We'll get into chapter 4 and we'll discuss some things about chapter 4. And then we'll see. I'm not sure if we're going to get into chapter 5 next week or not, but that's kind of where we're headed with things. We're going to jump into chapter 4. Okay. So make sure, and like I say, big thing, make sure that you've done enough homework, you've taken the exam, and that you're showing up to class enough that I can justify not dropping you from the class. It's part of my obligation. I'm supposed to drop people that are not on pace to finish the class successfully. Okay, so make sure you're doing that. As always, so I'm going to shut down the YouTube stream, but I will stick around in Zoom and answer any questions. So anyone who wants to talk to me, anyone who wants to ask about a homework problem or a way that the class works or something like that, come talk to me in Zoom, and I'm happy to chat with you. Otherwise, I will see you. What day is today? Thursday. It's Thursday. So I'll see you on Tuesday, I guess. Okay. Thanks, everybody.